So, as it's been alluded to, my name is Jonathan Pulsifer. I'm going to talk to you a little bit about how we do what I've coined infrastructure security 2.0 at Shopify. So, a little bit about me. I'm an infrastructure security engineer at Shopify, certified Kubernetes administrator, and I like to do some social things. So, please, I expect at least no less than 5 Twitter followers after this talk. No, I was joking. Previously, I was a team lead at the Canadian Forces Network Operations Center. I was a network defense instructor at the Canadian Forces School of Communications and Electronics, and I did some work for SANS for a little bit before jumping ship and going to Shopify. So containers. Who here knows or has heard of Docker? Hands up, please. That's a good portion of the audience. Who here runs Docker or containers in production? Hey, look at that. Maybe like 5, 10 people, right? So the cloud and these core cloud concepts, containers being sort of one of those, is really new to industry. So hopefully I'm going to be able to demystify some of these core cloud concepts. So for those of you who have heard of Docker and are running containers in production, who can tell me explicitly what a container is? Very few hands will go up as this technology is sort of misunderstood. Firstly, it's probably easier for me to talk about what containers are not. Containers are not first-class citizens or first-class concepts when it comes to Unix and Linux operating systems. They are not Solaris zones. They are not BSD jails. They're not virtual machines. More importantly, they are not real. Containers are real, but you just said that hands are up. And we know what Docker is. What does this actually mean? What's a container? Can somebody tell me what containers are made up of? Rhetorical question, I'm going to tell you. So containers, long story short, is OS-level virtualization. Containers are made up of a few different pieces, but before we can talk about these pieces, it's important to understand what makes up these containers. So you can see on the right-hand side, we have a graphic here detailing from Docker what a container is versus what a virtual machine is. And you can see the primary difference here is that the virtual machines rely on something called the hypervisor underneath. So a hypervisor, I'm not going to get into hypervisor theory or any of this, but TLDR, a type 1 hypervisor would be like your ESXi, your vSphere, your enterprise offerings from vendors, Zen server, for example. This really thin layer of abstraction to help you virtualize the underlying hardware on a given blade. Or in the case of a type 2 hypervisor, your VMware workstation, VMware Fusion. These things are type 2 hypervisors, and they virtualize not with a thin layer of operating system, with a full stack. So like what this means is that you're running VMware Workstation on your Windows computer. You have virtualized the hardware through that entire operating system, kernel included. So with containers, we take away that hypervisor, and on all the applications that are running inside of a given container are using the same kernel. They're sharing the kernel of the underlying host. And this is where we get to play with some really fun abstractions and really get to increase security posture. And we're going to talk a little bit about how that works today. So containers are made up of 2 distinct pieces, essentially. Namespaces, Linux namespaces, and control groups, or C groups. And we're going to step through some of these namespaces and control groups and try to identify which threats we can then sort of remediate while we employ these. So every time you spin up a container, what you're doing, if you're familiar with the Unix or Linux command line tool called unshare, we're creating this isolated, what's called a namespace in Linux. And a namespace is really the idea that an application will think that they are in their own little operating system. So what we're really doing is we are taking a global resource like a network driver or your user ID maps, and we're making them virtualized. We're virtualizing the operating system, and that's it's OS level virtualization. So here's a number of Linux namespaces by which we can then isolate a process or a number of processes inside of a container. So one of the easiest ones to understand is the user namespace, which isolates your user and group IDs. So what does this mean? If you are on a Linux workstation or a server, and you're UID 0, right? You are root, you are God mode. If you're UID 0 inside of a container, what actually happened when we broke this down into namespaces, is that we've mapped an ephemeral user ID, so user ID 12345, is going to then be user root inside of the container. So on your actual host, the host operating system that your container is running on, we have UID 12345 is actually what's going to be running the underlying process, whereas in the container, you're going to be assuming that you're root. And we can do this with a number of the different namespaces, so we can really isolate what a process can see. And that's really what a namespace is. It's sort of described as, what can my processes or what can my container see? So if we can isolate these primitives, we can also isolate them with control groups, what these processes can do. So this is where we have access to our CPU scheduler, we have our block I/O, we have our process ID list. You know, what's PID1 in a container is a sort of a whole other talk in itself. But with control groups, along with namespaces, we can provide sort of pseudo sort of the wrong context talking about Linux, but you can provide these isolation primitives around a number of applications. These are first-class concepts. These are concepts that are understood and provide direct access to given resources inside of your Linux operating system. And that really is what makes up a container. We've talked about Docker a little bit, and it's important for you to know that Docker is as much a technology or capability as they are a vendor. So the Docker container format is probably the most understood and widely used container format. They provide you a nice little interface to package up your applications and deploy them. So what we're going to do is talk about how we can build Docker containers securely. So the mission here is, as Shopify moves away from the traditional data center model into public cloud, these are the concepts that we have to be good at in order to succeed in the public cloud world. And there are challenges there, and we're going to talk about a few of those a little bit later on. But firstly, we need to talk about how we take that shared server approach and really break down our applications into, we're going to throw some buzzwords out there, into microservices. And we start with containers to do this. So when you're starting off in the Docker land, you have a number of what we call base images that you can build your applications on top of. And some of these should be familiar to you. The Debian, the CentOS, the Ubuntu. These are base images typically provided by the vendor, like Canonical would provide Ubuntu, for example, a minimal base install of libraries and folders that would give you a really a traditional feel, I guess. If you're working in industry and your primary operating system on your shared servers is Red Hat, I would not suggest to you that you start off building with Ubuntu containers, because those are not going to be familiar to you. The file system is going to be laid out a little bit differently than what you're used to. You'd probably want to start off with CentOS, right, where it's close enough to Red Hat. Something to note about this, though, is the image size. Typically, you know, in security operations, right, green is good, red is bad. CentOS isn't bad in this case. It's just a contrasting color, but it just so happens to be the largest container of the bunch. So if you start off building a CentOS container, you're going to be immediately starting with 197 megabytes of packaged dependencies and applications. Whereas if you start off with an Alpine, you're looking at about 4 megabytes, which is a huge difference when it comes to network throughput. When you start pushing and pulling these images, it becomes important. I would not recommend starting with a busy box if you're new to containers, because you'll find that a lot of your binaries are not there, and this will give you some extra headaches. This is probably the most simple Docker file that I could build. So when we build Docker containers, we are given these directives on the left-hand side from run and entry point. to run these commands against a Docker container. And you can see what I'm doing here is from Alpine 3.6, we're going to run APK. APK is the Alpine package manager. And we're going to add the snort package. And when we interact with this container, we're going to interact with the entry point pointing to bin snort. So every time that you run this container, this package of dependencies and applications, the first PID, the first application that we're going to interface with is going to be snort. Are we done? Is this it? Have we just deployed IDS across all of our cloud sort of infrastructure with this one Docker file? No. So just because it's easy to install applications in Docker, we should not avoid best practice. And this is probably the most important takeaway as end users to containers that I have for you today is just because you have this new technology afforded to you and you say, oh, John, like my application is isolated due to namespaces and control groups. You told me this, right? It's super secure. Wrong. What we have to do is still perform best practice. And you can see here the difference between what I would consider a bad Docker file versus a good Docker file. And we're going to talk a little bit about this good one. So what you've noticed that I've done at the beginning is I've added my users and groups so that when we run our applications, we can appropriately drop privileges so that we're not running as the root user anymore. Even though, remember, that it's not true root. We're root inside of a container, which is UID 12345 on the outside. The second largest piece, I mean, we're at a security conference, right? Security is important. Run APK upgrade, no cache. We need to make sure that our packages are always staying up to date, right? Security, patching is important. So because of this, you can see that the Docker file has grown from, that's not it, from 3 lines into a few. And this is probably the easiest example that I can give you of these Docker files. At Shopify, when we build a large container that supports like a Ruby on Rails application, for example, it is not 5 or 6 lines. It ends up being sometimes up to 100 to install all of your dependencies and stuff appropriately. We build a lot of containers at Shopify. When I pulled the numbers for this talk, we were building about 6,000 containers per day through our automated CI process, and we have about 330,000 images inside of our primary Docker repository. So me, as part of a 6 man and woman security team, how do we then stay on top of this security posture with such scale? And this is where we're going to introduce our builder. And this is the name that we've given our builder. It's called Pipa. And Pipa is a Docker in Docker sort of builder that's written in Golang that's deployed on BuildKite. For anyone who speaks Portuguese, Pipa means kite in Portuguese, and it runs on BuildKite, so that's where that naming comes from. What we can do with our builder is a couple fun things, but this is where security automation really comes into play. So as a developer, should you be responsible for provisioning underlying infrastructure? Arguably no. Should you be expected to understand Linux security primitives like capabilities, for example, or syscalls? Does that, if you're going to push out this application that, I don't know, checks the levels of the beer taps inside the cafeteria, which has been done, are you expected to know these things? Arguably no. So what we can do on the security team is enforce these same secure defaults at build time to really ensure that our containers are running at an appropriate, what we would call a security posture. So with Pipa, it will take a repository and it will look at all the files and it will make its best guess as to what type of container that you need on the other end. So if it sees a gem file, it probably need a Ruby container. If it finds like a package.json, for example, we need some like Node.js. If you provide a Docker file, we will skip all that guessing and just build the Docker file that you have provided. And this is some sort of automation that we get over here. On the right-hand side is just the GUI for our builder. But at build time is probably the time where we have the most context into what is running or being installed inside of a given container. And with this, then we can audit and start creating these checks that will allow us to automate our lives away, and we're going to talk a little bit about those. So what we can do at container build time is we can check for the presence of a user directive. If you remembered my bad versus good Docker file example, I specified the user, and what we can do is check for that to ensure that the container is not running as root, because I would consider that bad. And if we can check for this at build time, what better time to then alert the developer that something that they're doing may be not secure. We can check to see if this container has any vulnerable packages and make other attestations. So attestations are really fun. So when we're building a container, we can attest then that this container has been built by us. We can attest that it does not run as root. Since we keep all of our configuration inside of the source repository for an application, we can then audit the Kubernetes runtime. We can check their manifests and see how is this container going to be deployed. And we're going to talk about and introduce Kubernetes in a little bit. But we can ensure that then there are no regressions in any runtime security controls, and we can attest this. And this is where we introduce Grafeus and Credes. So Grafeus is an open source software component metadata API. String a bunch of buzzwords together and everybody understands. So what this means is that we have this the Spectoid API that is our central source for software component metadata. I don't say container metadata because it is so much more than that, but a container is just another piece of software that we can then generate and store this metadata with. And it's done by a key, so you have my registry or gcr.io or your Docker Hub, image.sha256. So we have this digest of this container. That means this is a unique container. And then we can provide a list of things like what packages are installed and push this up to a central metadata server. This is Grafeus. And then from that, we have this tool called Credes. And Credes is the governance engine behind Grafeus. It allows us to build a full story of a container with metadata as it runs through our build and deploy pipelines. And we can then enforce, based on the metadata stored in Grafeus, whether or not a container is allowed to be deployed to our infrastructure. And this is really powerful because for once, now, finally, we can ensure that every container that's run on Shopify's cloud infrastructure has in fact been built by us, which is really, really unique. So as an adversary coming into this cloud-native ecosystem, you find yourself on a Kubernetes box and you get access to the API somehow, and say, I want to start a new container with my bad tools in it. Let's pull down the Kali VM or the Kali container, right, for funsies. And if we can take that away, it really reduces our threat model there in saying that no one can spin up a container that can contain any arbitrary applications. No one can pull in an untrusted container. Every container that we build has to be trusted because we've secured it during the build. Now that's a little bit scary, right? There's talk about like supply chain attacks earlier, and we have to be a little bit more prudent with our internal security controls to make sure that a developer cannot inject some bad into a container, therefore then it is trusted when it comes at the other end. But this is the power of what we can do with these attestations. On the right-hand side here, this is a JSON blob. Everything is JSON and YAML. I call myself a YAML engineer now working with Kubernetes, and you'll find out why soon. But with this vulnerability information, we have a vulnerable package, TCP dump. TCP dump had a vulnerability in 4.9.0. It's actually fixed in 4.9.2. You can see on line 25. Since we have this CVE information stored in Grafeus, and we understand what packages have been installed on our Docker containers at build time, we can actually go through and create what's called an occurrence of a vulnerability that's found in the container so we can react a little bit more appropriately to it. So this really makes up a large piece of our container enforcement and governance. And check out the Shopify engineering blog. I wrote a technical blog on how this actually works. And we released it with Google a couple Thursdays ago, so that's pretty cool. They also have a blog, if you want to learn more. So how do we deploy containers? We know how to build them. We know what they are. But deploying them is that last piece to the puzzle. And this is where I get to introduce Kubernetes. So I'm not wearing my Kubernetes shirt. Right now I'm wearing my This Is Fine shirt, because typically everything's on fire, but we're all okay. And I have my sweater with me today, though. So Kubernetes is an open source, enterprise-grade container orchestrator, container scheduler. It makes sure that our containers run where we want them to run, how we want them to be run, and lets us do that in a declarative way. And we're going to talk about a little bit of Kubernetes architecture and how that works. So we have lots of servers at Shopify. I think our production is around 15,000 CPUs or something like this running in the cloud right now today. We have 2 data centers that are still very much hot, active, but we are in the move to a public cloud. We do have a bunch of different operating environments, but I'm going to talk about our new GKE Kubernetes environment today, because this is where all of the hype is. This is where all of the security, conformance, and governance exists. So we need to understand how this works. So Kubernetes, on GKE specifically, is made up of a number of distinct components. We have the master, and then we have the nodes. Nodes are sometimes called workers, minions, slaves, but we're gonna keep referencing them as nodes for these diagrams. And all these diagrams came from the Kubernetes basics. We're just gonna walk through it. So this Kubernetes master is TLDR, an API server that accepts commands and will do things based on the commands that you send it. The master has a few distinct components: the API server, the controller manager, which just sits in like a loop and makes sure that things are in a good state, or the state that you want them to be in, and the scheduler, which will determine which of these nodes to put your containerized workloads onto based on a bunch of given primitives. As we move into the abstractions made available to us in Kubernetes, we have something that's called a deployment. And a deployment specification is where we can say, hey, Kubernetes, run my Docker container in this way. And this is sort of what that looks like. You see that the deployment, the resource is actually held in the center, which is the master. It's held in the API server, again, in this declarative way. We spit them a JSON blob, and it stores it in etcd and reconciles against that. And what it's actually done, the scheduler has picked a given node to run this containerized application on, and this is what it looks like. And this is familiarizing yourself with with some of the shapes and architecture here. So as we dive into a node, there are a couple key processes that run on each of the nodes. And that's the kubelet. And the kubelet, what that does is that it accepts these commands from the API server and will do something based on that. Like say, for example, the Kubernetes API server would say, hey, kubelet on this node, run this workload. It says, OK, and it does the thing. Each node is also running Docker. There are a number of different container runtimes available, but for the sake of this talk, we're just going to choose Docker. So this is an example of Kubernetes pods. What a great time to step back and remember our container basics and to talk about these namespace and control group isolation techniques. So we have up here a bunch of Kubernetes pods. Because we're doing shared kernel OS level virtualization and are using namespaces, we have this cool technology available to us that lets us share namespaces. So you can see in 10.10.4, the largest of the pods here, we have a number of volumes, and we have a number of containerized applications. And it's all sharing the same IP address of 10.10.10.4. So this is using the underlying Linux primitives, your namespaces, to run a number of containers in the same namespace, so they both have the same IP address. And in this case, if you're familiar with Docker, this is where you're specifying the network. If you do Docker run tac-tac-net, and I want my containers to talk on the same network, this is what Kubernetes is doing for us. And this is the basic workload of Kubernetes. They're called pods. And a pod is made up of one or more containers and one or more volumes underneath the same Linux namespace. And this is what this looks like. The power of Kubernetes really shines with its labels and selectors. So what we can do now is if we have a number of given workloads on Kubernetes, we can then set a few labels. Say, maybe my environment is staging. Maybe my app's name is Nginx. In this case, we have two different services running, service A and service B, and they're both labeled. And we can then select those labels with selectors, label selectors, and then provide or do something with the result of that. And what this means is that up at the very top, you see this green outline. This is the label selector for app equals B. So it's selecting every container, every workload, every pod that's running with the label B. And because of this, we can then expose them. So we're going to step into this a little bit more, right? What are containers? Oh, here's Kubernetes. Uh-oh, how do we tie it all together? So here's an example of a really, really poor Docker file. And I say poor because it's an anti-pattern. Because containers are immutable, that is, once they are built, here's your checksum of the file system. This is it. It's not okay to do things like run SSH inside of a container, run sudo inside of a container, because we don't need to do this. Given the abstractions provided to us with Kubernetes and Docker, we should not be inviting persistence into an immutable cloud-native infrastructure. But, sort of do as I say, don't do as I do. One of the easiest examples for me to provide to you today about these container security abstractions is to give you a Docker file like this. So I built a Docker file, or I built a Docker container based on Debian Stretch. And what I've done is I've added myself a user, and I've done my due diligence, I've done my updates and upgrades, I installed sudo, and then I added myself very securely to the sudoers file inside this Debian container. If you haven't figured out, my password is in fact password. And I dropped privileges just because that's the prudent thing to do. But I'm going to show you what we can do then with Kubernetes security controls to really take advantage of these abstractions today. So here's your first introduction to a Kubernetes manifest. We talked about Kubernetes, this minion versus node, how do workloads get scheduled on nodes. We talked about pods, what a pod is. This is how you define a pod in its most simple form. So this is why I call myself a YAML engineer. Working inside Kubernetes for the last year and a bit, I've seen a lot of these manifests, and most of my work is involved in maintaining or securing these manifests. So this is where we say, here's a pod, its name is sudo, its environment is staging, there's some labels that I mentioned before and why they're important. Inside of this pod, we're going to run a container. There's where we get the container from my Docker hub, and this is the command that we're going to run against this container. So we take a step back and see that I didn't provide any entry point to this container, no process to run my arguments against. What it would do is inherit from the parent image. So I pulled from Debian Stretch, so it's going to use the entry point of Debian Stretch, which is just the shell, and I'm going to tailf dev null. That means the container will stay up forever until I turn it off. The piece that matters the most is highlighted in yellow at the bottom, and this is the security context. The security context in Kubernetes allows us to further explore these isolation primitives that I mentioned at the beginning of the talk, and we're going to talk about how they work. So in this case, allowed privilege escalation is set to false. Allowed privilege escalation is a new knob to turn in Kubernetes 1.8, which essentially, for those who are familiar with Linux and Unix, applies the no new privs allowed on your workloads. So what this means is that setting this to false, when Kubernetes runs this, it will apply the no new privileges flag. So when you try to do something like, I don't know, sudo inside of your container, you get a sad phase. So here's just an example of how we would deploy an application on Kubernetes using this manifest. Let me digest that for a second. Take a step back. We have this pod.yaml, and we're going to create it against our Kubernetes. So I'm talking to the API server on the master. It says, I want to create this workload, do the thing. Then I made sure to get the pods, as in give me a list of all the pods that are running, and please show me their labels. And that's what I did in the second command. And you can see that app sudo environment staging. And then I entered the pod, and I did a uname A, just to show you that, look, there's the kernel that I'm running on. You see my name at sudo, implying that privileges are dropped. I tried to run it, and I get this gross error message. The only reason that this gross error message occurs and that I cannot switch to UID 0 is because of that allow privilege escalation false flag. Had I precluded and not included that directive, I would be able to get root inside of my container using the sudo command. But this is where we start defining security posture in the cloud. This is called a pod security policy. A pod security policy in Kubernetes is a cluster-level resource that allows us to define our security controls in the cloud. And there are a lot of options available to us. I don't need to step through them all. Hopefully a lot of them make sense, but I will highlight the host IPC, host network, and host PID. These are these namespaces that you can share with the host, and you have to think that if your host, your Linux blade, running an arbitrary kernel and hosting a bunch of Kubernetes containers, all the workloads running on that host are using that same kernel, right? So you have to be very careful running any sort of multi-tenancy inside of your Kubernetes clusters today, because if a developer, for example, switches the host network flag to true and starts using the underlying host network of your node, they could potentially open up some ports, do some bad things, do some network level attacks, capture your traffic. If we supply a pod security policy such as this, they would not be able to do that, and then we can therefore ensure the security of our underlying nodes. We've been on the cloud security team playing a lot with capabilities over the last, I don't know, year or so. So capabilities are your UID 0 on a Linux workstation. You can do all the things, right? You are root. In like Linux 2.6 or something like this, they've created the ability to break down the privileges that root has available to it into what's called capabilities. And then because of the abstractions that are provided to us through Docker and Kubernetes, we can then drop specific capabilities. It's important to note that Docker doesn't do all this by default. Defaults are not okay. So these are the capabilities that are actually allowed by default in Docker containers. So if you run a Docker container right now and you set your net to your host that is sharing the same namespace as your host, and you leave the net raw capability on, then that means that you could do things like run TCP dump and start doing network level attacks and these sorts of things. There are other capabilities that are important, like DAC override, for example. DAC override is discretionary access control on Unix. And what this means is that if we take this capability away, the root user in a Docker container can no longer make arbitrary changes to the access control models. Like the root can then not enter your home directory, for example, if the DAC override capability is taken away. It has to then respect those access controls. If we drop all these capabilities over here on the right-hand side, your root user in your Docker container can't even ping, right? They can't open a port, they can't bind a service, they can't interact with special devices or files, they can't chown anything, you've really hamstringed root here, right? So think about this as an adversary. You're prodding a system, you find that this server, as you think it's a server, is running a vulnerable version of Apache for funsies. And you do your Metasploit wizardry, and you craft an exploit, and you bust into that container, and you get a shell, and your user Apache or www on this box. You then have to somehow escalate privileges to root, right, to maintain persistence. Just say that you could do that. Just say that you could escalate privileges from root inside of this host, or to root inside of this host. But then you realize that you're in a container running on Kubernetes that has all these capabilities taken away for it. What can you do, right, as an adversary? If we're running with read-only root file system true, I mean, then you can't even download your tools into the temporary directory, right? If you can't open a socket, if you can't do anything that you'd expect that you could do as an adversary, kind of SOL, right? I mean, in this case, you can't do much, so you just leave. In the case of Docker and Kubernetes, maintaining persistence is very hard because nodes have problems, nodes go down, Kubernetes reschedules the workload, and persistence is sort of handled already by Kubernetes. What we can do is actually introduce other ways of mitigating this risk, like if anyone has heard of chaos engineering from Netflix, this is something that we do also at Shopify, where we will take a container that has been up, say, longer than a day, and we'll kill it. Why? Reasons, right? It's to maintain, it's to get rid of that threat of persistence, right? If an adversary has maintained persistence on a Docker container, if we kill all of our containers every day, then we don't really have to worry about that. Every day is sort of arbitrary, right? But you get the point. We can do this with not only containers, but their underlying nodes as well. Because we're on the cloud, we have these things called managed instance groups that will make sure that, say if you have 5 servers of the same likeness, if you delete one goes down, it'll bring it back up, right? So this is the kind of, these engineering wins really reduce overhead and allow us to really unlock our velocity and solve problems in a different way. And using methods like this and some chaos engineering really affords us some big wins here. Aside from all of this, right, we've taken away the capabilities from the root user. We've taken care of the persistence aspect. What else then can we do? Well, we can still use some Linux security modules that are built into the kernel to help us further restrict the operations that can be done inside of a container. And this is an example of an AppArmor policy. And we're running AppArmor on all of our nodes in the cloud today. And this is an example policy that will deny all file writes. So you couldn't write to any file even if you wanted to. And this combined with a read-only root file system, we have great trust that nobody can do bad things inside of our containers. And what you would do here when you have this policy is you would apply it in the same fashion using a Kubernetes manifest as you see here today. So we have an annotation. It's a little bit different than a label. I won't really go into it. But it says, please apply this AppArmor policy to the container named Sleeper. And the container named Sleeper is just a BusyBox container that's going to sleep for an hour and then die. They're just proving an example that we can take this AppArmor policy and apply it to a container. Further to this, we have SecComp, or Secure Computing Mode. It's the idea that you can take an application and it will enter this secure state, and it won't be able to make any syscalls, less a few that have been whitelisted against already open file descriptors. TLDR, we can take away syscalls from applications too. So along with like application level AppArmor stuff, we can take away the system calls that this container can make. It's important to note that the default Kubernetes runtime for SecComp is actually unconfined. So we're not actually restricting any syscalls inside of Kubernetes workloads by default unless we do something like this. This is a very short example. Brevity is important for slides like this. In this case, we're taking away the ability to get the current working directory and chmod. So inside of a container, if you can't chown, you can't chmod, you can't access directories that you're not allowed to, you can't write to the file system, you can't open a socket, these sorts of things, you kind of get the idea that the posture is actually pretty good. In Alex Arndt's presentation this morning, he made a little reference to rmrf/ on a file system, aka delete all the things. If we didn't have containers, we would have to consider this. But because we have containers, now we don't. And because containers are immutable, if we can provide, say, a health check to make sure that a given file is present on a container or the container is responding to pings or something, what Kubernetes would do, if I went in there and fat finger deleted everything on the container file system, Kubernetes would then recognize this and create a new container with the same file system as before. So we don't have to worry about these problems. Given read-only root file system, I can't even rmrf/ if I wanted to, right? So this is pretty cool. This is where the wins are coming from. And this is how you would apply the same seccomp profile to another running container. You see I'm running this against a container named persistence, and persistence is running tailf null. It's important that a container stays up. And if you don't provide a directive or some arguments to then ensure that a container stays up, either with tailf null or preferably some sort of foreground workload, like an Nginx or a Rails server, something like this, if the underlying application exits, your container will also exit under this loop, and it's a bad thing, and this is fine. So what? Shopify's grown a lot in the last number of years. I joined in January 2016 after I left the Army, and I think 72, 73% of the entire company has since joined after me. Member of a 6 or 7-man security team, a person security team. We have 2 rock star women on the team now, which is awesome. So what? So what about containers? What is this cloud hype all about? You have to take a step back and realize what you have to be good at to run a business. So because Shopify is over 500,000 merchants and we do a lot of transactions, a lot of money flows through, should we be good at securing our infrastructure? Yes, right? Would anybody then trust us to be able to handle their credit card information if we were not good at security? No, they would not trust us. I would consider that a core competency of Shopify, being good at securing infrastructure, being good at securing applications. Can the same be said about running a data center? Is running a data center a core competency at Shopify? Should it be? Arguably, no. As we move to the public cloud, it's implied that we found somebody else who's better at running data centers than we are. Because of this, we can take advantage of their engineering and their products and allow ourselves a little bit more freedom to develop these new technologies and new ways of solving security problems in the cloud. And this is the idea that I want to pitch for you today. That containers are not new. They've been around. C groups, control groups have been in the kernel since 2006, I think. A couple of Google engineers put the control groups in there, which is super cool. Containers, LXC, for example, has been around for years. And Docker is not unlike LXC, but because of these, it's like a paradigm shift in computing again, right? When virtualization was a thing, everyone said, oh man, get rid of the shared servers, let's put everything virtualized, and it's gonna be awesome, we have this isolation. Turns out like it's pretty bloaty, right? And it's almost like a regression to OS level virtualization, I find, but leveraging these abstractions really allows us to solve problems in a different way. And this is what I'm pitching. So here's an idea of the cloud platform at Shopify. We have a service which you interact with called services.db, which you say, here's my repo, and this contains all of my source code for my given service. And we say, click next, next, next. You get an automated pull request into your repository that says, hey, you want to join the cloud. Here are your Kubernetes manifests that allow you to run your workloads on our servers, which is awesome. And they contain the capability drops, the security context stuff that we all saw a little bit earlier. We build the container with our builder named Pipa. See up at the very top, there's a little build kite into Docker. We store that in our container registry on Google. And when we deploy, we have an open source deployment tool called Ship It. And it's just like at Shopify, we're a big Ruby shop, right? Or Shopify, the core application is Ruby on Rails. So, and we've gotten into the habit of wrapping everything in Ruby because reasons. So kubectl or Kubernetes deploy is a Ruby wrapper for kubectl that gives us a lot of automation wins and prettiness out of deploying applications to Kubernetes. Clear pass-fail results, doom detection, exposing of the correct logs. So what we've really tried to do is And that's the mission of production engineering at Shopify, to provide resilient, scalable, secure infrastructure for developers to deploy their applications to. And this is what it all comes down to. So after we deploy to Kubernetes, we have some other automation that kicks in, and we talk to some other GCP services. This is a whole other talk in itself. If anyone's going to Sector next week, I'm actually giving that talk there. Giving it also at KubeCon in December. So if you want to catch that about the cloud platform, more automation, that's coming up. But that's it. I welcome any questions. Thanks.